Welcome back friends, welcome back in another video tutorial for microbiology with Shagnik. So today in this video tutorial we will going to do a revised session on enzyme inhibition. Here we will going to talk about all the types of enzyme inhibition that we have discussed in our previous separate videos. A one video for everything related to enzyme inhibition. So let's get started with this video. So the first topic for discussing the enzyme inhibition should be the modifier of enzyme. What do you mean by modifier of enzyme? So modifier may be a organic molecule or inorganic molecule that have the ability to either positively affect or to negatively affect the enzyme activity. If that modifier have the ability to positively affect the enzyme activity, we will call it positive modifier or activator. If it going to affect the enzyme activity negatively, then we will call it negative modifier or inhibitor. Okay, and in this video lecture session, we will going to focus on the negative modifiers, that is the inhibitors. So inhibitor may be both organic molecules as well as metals, whereas positive modifiers mainly are metals. So the process by which negative modifiers adversely affect enzyme activity, we will call them as inhibition. So here we will going to talk about mainly two type of inhibition. One is reversible inhibition and irreversible inhibition. And the classification of inhibition is mainly done depending on whether the EI complex means enzyme inhibition complex, dissociates slowly or rapidly. Remember, if enzyme inhibition complex dissociate rapidly, we will call that particular inhibition as reversible inhibition, and if enzyme inhibition complex dissociates slowly, we will call it irreversible inhibition, right? So that's the idea. So we will going to start our discussion from reversible inhibition. So what is reversible inhibition? So reversible inhibition means in this type of inhibition, the enzyme and the inhibitor will going to interact with each other by reversible non-covalent interactions. Okay, and this reversible non-covalent interaction may be hydrogen bonding, hydrophobic interactions, or ionic bonds. Okay, now they are usually weak bonds, we all know, but when too many amount of reversible non-covalent interaction occurring at a single time, it will together create a strong impact. Okay, so that's the idea. So we can classify reversible inhibition on the basis of whether they are binding to the active site of the enzyme or they are binding to some another site, whether they are binding with the free enzyme or binding with the enzyme substrate complex. On the basis of those things, we can classify reversible inhibition into three different subtypes of inhibition. One is competitive inhibition, another one is non-competitive inhibition, another one is uncompetitive inhibition. So let's start our discussion on competitive inhibition. So this is competitive inhibition. So in competitive inhibition, what will occur? Remember, the inhibitors which will going to do competitive inhibition are known as competitive inhibitors, and competitive inhibitors looks like substrates, meaning that the competitive inhibitors have structural homology with substrates, and that's the reason why this competitive inhibitor may bind with the active site of the enzyme instead of the substrate if that particular inhibitor have higher affinity for that particular active site in comparison to that particular substrate. Okay, and as a result, what will happen? Enzyme inhibitor complex will form instead of enzyme substrate. Now what will going to be the solution of it? If we going to reverse the competitive inhibition, then we have to increase the concentration of the substrate, okay, so that it can fight with the inhibitor for that active site, right? So that's the idea. So you can understand it such a way. Suppose you are fighting with someone who is more powerful to you. Now what you can do? You can call your friends to join you to fight with that particular person, right? So that is the idea. So this is the figure for reversible inhibition. In reversible inhibition, not only the figure of reversible inhibition, but it is the figure for competitive inhibition. So in competitive inhibition, what will occur? As you can see, inhibitors join with the enzyme and leads to the formation of enzyme inhibition complex. Right. Now here the rate constant, as you can see, Ki is the constant for the formation of enzyme inhibition complex. Right. So sorry, this K1 is the constant for the dissociation of EI. Okay, and that's why we have written the value of Ki according to our chemical formula, product by reactant, right? We are using this formula from the chemical kinetics, that is product by reactant. So product here will be EI individually divided by concentration of enzyme inhibition, right? So that's the thing. So here you can see, by further inputting more amount of substrate, we can remove that particular inhibitor and go back to the enzyme substrate complex, right? So that is the figure for competitive inhibition, and this is very important to remember competitive inhibition easily, right? That inhibitor will going to bind with the enzyme to get enzyme inhibitor complex, and this enzyme inhibitor complex can be reversed to enzyme substrate complex if you going to give too much amount of substrate, right? So that's the idea. So as I have told you that the formation of EI can be reversed by increasing the concentration of the substrate. Now let's look at this picture, because here we will going to measure the change of the kinetic parameters, various type of kinetic parameters. We will going to see how various type of kinetic parameters such as Km, Vmax will going to change in case of competitive inhibition. So let's try to think about what I have learned or what I have taught you during our discussion on enzyme kinetics. We have discussed about the Km, right? What I have told you during those videos about Km. So Km is inversely proportional with the affinity of the enzyme for the substrate, right? That means if enzyme substrate complex forms, then Km will decrease, right? So that is the idea. So now what you can see that due to the presence of inhibitor, enzyme inhibitor complex are forming, right? Enzyme substrate complex is not forming, right? So what we can say? We can say that Km will going to increase, right? And remember one thing, to measure whether Vmax is changing or not, just remember one thing, if inhibitor will going to interact with enzyme substrate complex instead of enzyme, or along with that enzyme, then remember that Vmax will going to change. Okay, and most of the cases Vmax will going to decrease. Okay, just remember it. If you want to measure Vmax, just saw in the figure whether the inhibitor is reacting with enzyme substrate complex or not. Okay, so that is the idea. So in competitive inhibition, Km will going to increase. As you can see that enzyme substrate complex is not forming, that means the affinity of the enzyme for the substrate is decreasing, right? And Vmax will go into unchanged, right? So that's the idea. So here you can see. Okay, now the second thing we have to learn from the competitive inhibition is the Lineweaver Backplot. Okay, so the Michaelis-Menten equation for the competitive inhibition will be V0 is equal to Vmax into S alpha Km plus substrate concentration, right? You can remember it with the help of the thing that I have told you that Km will going to increase, right? So something will going to multiply with the Km, and this something is alpha. Okay, and the value of alpha is 1 plus I by Ki. Now if you going to take the reciprocal of this Michaelis-Menten equation, you will get the Lineweaver-Backplot equation for your competitive inhibition. Okay, so that is the equation. So now we are going to analyze the Lineweaver-Backplot graph for competitive inhibition. So here you can see the black line is for normal reaction where inhibitor is not present, and blue line is for, or here I am marking it with green line is for when inhibitor is present. Now, how you can understand? Remember what I have told you. I have told you that during competitive inhibition, Km will going to increase and Vmax will going to remain unchanged. Right? Now focus on this thing. Now let's consider minus 1 by Km, which is the intercept for enzymatic reaction in absence of inhibitor. Let's consider the value of minus 1 by Km is minus 5. I am changing the color so that you can visualize it well. So minus 1 by km, the value of minus 1 by km is 1 minus 5. Okay. So now if we're going to solve this equation, so we will get the value of km will be something like 1 by 5, right? And the value of 1 by 5 will be 0.2, right? So now this is the intercept of x-axis for when inhibitor is present. Now let's consider the minus 1 by km as it is more closer to 0. So we can say the value of minus 1 by km is 2. Okay. So by solving the equation, we can get km for inhibitor is present is 0.5. Okay. So you can clearly see that when inhibitor is present, the value of km is 0.5. But when inhibitor is absent, the value of km is 0.2. And you can clearly understand that the km when inhibitor is present is far more larger than the 0.2, right? So that is the thing. So here you can understand that why the inhibitor containing enzymatic reaction line is closer to the 0 than the line which is for enzymatic reaction in absence of inhibitor, right? And here you can see that the y-axis intercept, which is 1 by Vmax, is same for both the cases, right? Because what I have told you that Vmax will going to unchange, and that is the indication of it. Okay, and slope will be here Km by Vmax, so that is the thing. So I hope you can understand the concept of competitive inhibition. Now let's come to the example of competitive inhibition. So first example, now let's go back to the concept of competitive inhibition. In competitive inhibition, the substrate and inhibitor will have some structural homology, right? So you can see the succinate, which is the substrate for succinate dehydrogenase, looks similar with the malonate, which is the competitive inhibitor for that particular reaction, right? So malonate is the competitive inhibitor for the conversion of succinate to fumarate, and it is a very, very important reaction from the point of view of tricarboxylic acid cycle or Krebs cycle. We have already discussed in our carbohydrate metabolism playlist, right? So that is the idea. Along with that, sulfonamides, which is also another important competitive inhibitor of PABA, that is para-aminobutyric acid, during folic acid synthesis. Okay, so sulfonamides and malonate are the two examples of competitive inhibitor. So that is the ending of competitive inhibition. Now let's talk about uncompetitive inhibition. Uncompetitive inhibition, as its name suggests, there will be no competition between the substrate and the inhibitor. Okay, why there is no competition? Because inhibitor, instead of interacting with the free enzyme, it prefers to bind or interact with the enzyme substrate complex. Okay, so here it is clear that when we will going to do the measurement of kinetic parameters in case of uncompetitive inhibition, we will going to see that the value of Vmax will going to be changed, right? And now as inhibitor here will going to interact with enzyme substrate complex, there is no doubt that we cannot reverse this reaction by just increasing the concentration of the substrate, right? Because here enzyme substrate complex is already formed, right? Then inhibitor is going to react. That means inhibitor will going to bind with some other portion of the enzyme instead of the active site, right? So that is the thing. So now if we going to measure whether Km will going to decrease or increase or unchanged, and what will be the effect in case of Vmax. So first we have to see the figure, right? So here you can see that inhibitor is interacting with the enzyme substrate complex, giving us enzyme substrate inhibitor complex. Here the constant for the dissociation of enzyme substrate inhibitor complex is K2, right? Now see it very carefully. That is, here the value of Km will going to decrease. Now you may ask why? Because remember, when uncompetitive inhibitor is present, the equilibrium for enzyme substrate complex formation as well as enzyme substrate inhibitor complex formation will going to shift towards the product. Okay, and according to La Chatelier principle, that simply indicates that the affinity for enzyme for that particular substrate will going to be increased in presence of uncompetitive inhibition. You may remember just one thing, that in case of uncompetitive inhibition, due to the presence of uncompetitive inhibitor, the affinity of the enzyme for that substrate is increasing, right? And what I have told you, if such kind of situation will occur, then clearly Km will going to decrease, right? So that is the thing. Along with that, as I have told you that here inhibitor will going to interact with enzyme substrate complex, clearly here Vmax will going to change, and I have told you that most of the cases Vmax will going to decrease. So Vmax will going to decrease. Okay. So that is the thing in case of uncompetitive inhibition. So here the Lineweaver Backplot equation, before that the Michaelis-Menten equation for uncompetitive inhibition, that is V0 is equal to Vmax into S Km plus alpha dash S, right? So that is the thing. So here now Lineweaver Blackplot equation for uncompetitive inhibition. So just by taking the reciprocal of the Michaelis-Menten equation, we can derive this equation. There is no issue. So now here this is the graph for our uncompetitive inhibitor. So here this is the normal case when inhibitor is not present, and these two case is for when inhibitor is present. Okay, here the first one is for when the amount of the inhibitor is quite less than the next one. Okay, where the amount of the inhibitor is quite high. Okay, so now let's try to remember what I have told you, that in case of uncompetitive inhibition, Km will going to decrease, Vmax it will again going to decrease, right? So now let's consider a situation that here the intercept for the reaction when inhibitor is not present. Here let's consider the value of this minus 1 by Km is minus 2. So by solving the equation, we are getting what? We are getting 0.5, right? Now minus 1 by Km app, which is the value of Km when inhibitor is present, let's consider the value is minus 5. So by solving this equation, we are getting Km app is 0.2, right? Here it is clearly seen that the Km when inhibitor is present is lower than the Km when inhibitor is absent, right? And that is what I have told you, that Km will going to decrease, right? And if we consider the case for Vmax, now let's consider this Vmax, 1 by Vmax when inhibitor is not present is 2. Okay, so Vmax will going to be 0.5, right? Now let's consider this Vmax, which is for Vmax when inhibitor is present is 5, then the value of Vmax will be 0.2. Here you can again see that the Vmax when when inhibitor is not present, the value of Vmax is higher than when the inhibitor is present, right? So that is the idea, and that is the graph for our uncompetitive inhibition. Okay, so that is the idea. So in competitive inhibition, you can see that when so that is the normal line for when a inhibitor is not present, right? And Then now when we will going to use the inhibitor, the graph will be something like this. This is the competitive inhibition graph, right? And when we will going to see the uncompetitive inhibition graph, here the normal line will be this thing, and then the when inhibitor is present, the line will be like this. Okay, so that is the uncompetitive inhibition. So now when we will going to talk about the example of uncompetitive inhibition, so here the example is hydroxymalonate, which will going to prevent the conversion of L malate to oxaloacetate. Okay, here it is inhibiting the enzyme malate dehydrogenase. Okay, so another important uncompetitive inhibitor is inhibiting the enzyme ATPase, which is responsible for hydrolysis of ATP, is the excess amount of ATP, right? So here the idea is when excess amount of ATP is present, the substrate which is ATP and Mg, because you know that Mg here will going to play a very important role. So here the excess amount of ATP will going to react with the substrate and form a twice complex called ATP Mg ATP, and as a result ATPase cannot degrade the ATP. Okay, so that is the idea of uncompetitive inhibition and their examples. One is the conversion of L-malonate to oxaloacetate, which is catalyzed by malate dehydrogenase, is inhibited by hydroxymalonate. Another one is ATPase enzyme, okay, which is inhibited by high amount of ATP or excess amount of ATP, that is form a twice complex with the substrate ATP-Mg. Okay, so that is the idea. So this is the ending of uncompetitive inhibition. Now let's talk about non-competitive inhibition. Okay, so non-competitive inhibition is literally a mixture of uncompetitive inhibition as well as competitive inhibition. So here, if we going to directly see the figure for non-competitive inhibition, you can understand that here inhibitor can bind with the free enzyme as well as inhibitor can bind with the enzyme substrate complex, right? That means literally it is a mixture of competitive as well as uncompetitive inhibition. Okay, here the dissociation constants Ki and K2 will going to be very important. Okay, because if the K1 and K2 will going to be of same value, we will call it as pure type non-competitive inhibition. But if it is K1 is not equal to K2, then we will call it as mixed type non-competitive inhibition. Okay, so here the Michaelis-Menten equation for non-competitive inhibition will going to be mixture of uncompetitive as well as competitive inhibition. So it will going to be the both alpha as well as alpha dash will be present. Alpha dash will be the case for uncompetitive inhibition and alpha will be the case for competitive inhibition, right? So you can see that here up to that part, if we going to remove that alpha dash, then it will going to be a Michaelis-Menten equation for competitive inhibition. And if we going to remove this alpha and we going to add alpha dash only, then it will become a Michaelis-Menten equation for uncompetitive inhibition, right? Now by simply taking the reciprocal of this equation, we will get the Lineweaver Backplot equation for uncompetitive for non-competitive inhibition. Okay, so that is the idea for our non-competitive inhibition. Now what about the kinetic parameters, that is Km and Vmax? So here you can see inhibitors interacting with enzyme substrate complex. So clearly Vmax will going to decrease. Now Km, what will going to be the case of Km? Now remember I have told you that this non-competitive inhibition is a mixture of competitive as well as uncompetitive inhibition. Now try to remember what happens in case of competitive inhibition. In case of competitive inhibition, Km increased, right? And in case of non-competitive inhibition, what happens? Sorry, in case of, try to remember what happens in case of competitive inhibition. Km increases, right? And now try to remember what happened in case of uncompetitive inhibition. Km decreases, right? And as I have told you, it is a mixture of competitive as well as non-competitive inhibition as well as uncompetitive inhibition, then in case of non-competitive inhibition, remember the effect of competitive as well as uncompetitive inhibition will going to create a combined effect in KM that will give us the idea that in case of non-competitive inhibition, KM will going to be unchanged, right? If I try to simplify it, just try to see here inhibitor is going to interact with the enzyme, right? That is the free enzyme. That means clearly here KM will going to increase, right? Similarly, binding of inhibitor with enzyme substrate complex, from the learning of uncompetitive inhibition, we can clearly understand that here Km will going to decrease, right? So these two value will going to nullify each other, okay? And that is why in case of uncompetitive inhibition, Km, sorry, it is the non-competitive one. I am constantly confusing with competitive, uncompetitive and non-competitive inhibition. We are talking here about non-competitive inhibition. So here, as you can see, that in non-competitive inhibition, the two effect of Km neglify each other, right? And that is why Km will remain unchanged. Okay. Now Vmax will going to be decrease, right? Because I have told you that it is a combined effect of competitive as well as uncompetitive inhibition. Okay, so that is the idea. So here Km will going to be unchanged and Vmax will going to be decreased. Okay, so this is the Michaelis-Menten equation. So by taking the reciprocal of it, we will derive the Lineweaver equation, right? So now here in the graph of Lineweaver backplot, this line is for normal condition when inhibitor is not present, and this two is for when inhibitor is present. Now let's consider the first 1 by Vmax value, which is when enzyme inhibitor is not present, is 2. Okay, so by solving the equation, we can get the value of Vmax will going to be something like 0.5, right? Now, if we going to consider the 1 by Vmax value when inhibitor is present is 5, because it is located at quite upper position than the Vmax for our when inhibitor is not present. So now by solving the Vmax, we will get the value is 0.2, right? So clearly we can see that the Vmax when inhibitor is present is 0.2, and the Vmax when inhibitor is not present is 0.5, right? That means Vmax is decreasing, right? And here you can see that Km will going to be unchanged, right? So that is the idea of our non-competitive inhibition. So examples, various type of metals will going to play the role of non-competitive inhibition. Okay, for example, Ag plus, Hg2 plus, Pb2 plus, they will going to act as a non-competitive inhibitor for enzyme having SH group in their active site. Okay, for example, urease. Okay, so that is the idea, and we all know what urease can do. It will convert urea into ammonia, right? So here this type of reaction will be blocked by non-competitive inhibitors. Along with that, catalase peroxidase enzymes who have iron containing in their enzyme will going to be non-competitively inhibited by CN and H2S. Okay, so that is the idea of non-competitive inhibition. So we have completed all the three type of reversible inhibition: competitive, non-competitive, uncompetitive. Now it is time for irreversible inhibition. So irreversible inhibition, as its name suggests, here the activity or the effect of the inhibitor will not going to be reversed, right? So in case of irreversible inhibition, what will occur? The active side of the enzyme will going to react with the inhibitor via a covalent interaction. Okay, and that is the reason why, or that is one of the reason why we are calling it irreversible inhibition. And the main reason is here the inhibitor, by reacting with the enzyme, it will going to either modify the enzyme or it will going to destroy the functional group present on the active side of the enzyme. Okay, and that's will going to be the reason why we are calling irreversible inhibition as irreversible inhibition, because here it will going to covalently modify the enzyme, or it will going to destroy the active site present at that particular enzyme, okay, or the various type of important functional group present at the active site of the enzyme. So now if we going to see the figure, in that case you can see that inhibitors first will going to play a reversible non-covalent interaction, giving us enzyme inhibitor complex as well as enzyme substrate inhibitor complex. Now I want to told you one thing, that up to that point we can reverse the effect of irreversible inhibition with the help of another reversible non-covalent interaction, with the help of a inhibitor who have affinity for the active site of the enzyme much higher amount than the inhibitors that are doing the irreversible inhibition, or we can use the substrate having higher affinity for the enzyme as compared to that inhibitor, okay. But if we somehow fail to prevent the irreversible inhibition in that point, then everything will going to be out of the hand, because now this enzyme inhibitor and the enzyme substrate inhibitor will going to react covalently and will going to form a dead in complex, which we have here mentioned as EI star, okay. Now you cannot do anything to reverse this, okay. So here this is the idea of irreversible inhibition. So here we will not going to talk about how the kinetic parameters will going to change here, because here it is irrelevant. We have to learn about the change of the kinetic parameters, especially for reversible inhibition, right? But in case of irreversible inhibition, one thing is very important, that is the your examples. For example, iodoacetamide. Iodoacetamide is the irreversible inhibitor that will going to react with enzyme having SH groups in their active site, for example cysteine, okay, and that is the reason why we can use iodoacetamide for the detection of SH group, okay. Another important example is the diisopropyl fluorophosphate, okay. This kind of organophosphate will going to have the ability to react with enzyme having OH group in their active site. OH group means, let's consider serine, okay. So here an important enzyme which is important for nerve impulsion, for example acetylcholine esterase, will going to be inhibited by diisopropyl fluorophosphate, and that is why we are calling diisofluorophosphate as nerve poison, okay. So that is the idea. So diisopropyl fluorophosphate as well as iodoacetamide. Iodoacetamide will going to interact with the enzyme having SH group in their active site, and diisopropyl fluorophosphate will going to interact with enzyme having OH group in their active site, okay. So that is the case for irreversible inhibition. In non-competitive inhibition, we have seen various type of metal ions, for example your Hg2 plus, Pb2 plus, Hg plus, acting as a non-competitive inhibitor, especially for the enzyme having SH group in their active site, for example UDS, right? And then we have also seen the example of cyanide and hydrogen sulfide, that is H2S and CN, right? That will going to act as a non-competitive inhibitor for enzyme having ions, for example peroxidase catalase. So that is the thing of non-competitive inhibition. After non-competitive inhibition, in competitive inhibition we have, sorry, before non-competitive competitive inhibition we have also discussed uncompetitive inhibition. So in uncompetitive inhibition, ATPase enzyme is inhibited by excess amount of ATP, we have talked about this, and hydroxymalonate, right, that inhibit the conversion of malate to fumarate, right? So here the malate to oxaloacetate reaction is inhibited by hydroxymalonate, by which are especially inhibiting the malate dehydrogenase enzyme. So now in the very first one, that is the competitive inhibition, we have seen that various type of inhibitors that looks like substrate, for example the malonate things we have seen that inhibiting the conversion of succinate to fumarate is an example of competitive inhibitor, right? Along with that, we have also seen the sulfonamides, right, which was the competitive inhibitor of PABA during folic acid synthesis. So that is the various thing. So if I going to give a suggestion of enzyme inhibition from the enzyme inhibition topic, you have to learn only few things. One is what will going to be the change of kinetic parameters in case of competitive inhibition as well as uncompetitive inhibition and non-competitive inhibition. That is the first thing you have to learn. What will be the Michaelis-Menten equation for competitive, non-competitive as well as uncompetitive inhibition? Then what will going to be the graph for competitive, non-competitive as well as uncompetitive inhibition? That is the first thing, as well as the example of competitive, uncompetitive and non-competitive inhibition. So that is the thing. And in case of irreversible inhibition, you have to learn about the examples very, very importantly, and that's it. So that is the few things you have to learn from enzyme inhibition to answer any question from any MSc entrance point of view or any kind of PhD entrance point of view. So that is the complete total sum up of enzyme inhibition. So I hope this video will going to be very, very helpful for you. So thank you for listening to this class.